Let me share my slides here. All right. So are you able to see my slides here? This is the heat transfer course ME2005. I shared these slides with you in the Teams itself. Yesterday I have shared these files, so you can access these files. So two files I have shared. One is the syllabus, and other one is the slides. All the slides for entire course. So there are about 370 slides for the entire course. All modules included, including the uh, numericals. So everything is there in those slides. So the module 1 is about the fundamental concepts. So we shall see these fundamental concepts now. Heat transfer is thermal energy in transit due to spatial temperature difference. So this is the fundamental definition of heat transfer. So whenever we say heat transfer, we are speaking about thermal energy. There are several forms of energy. Thermal energy is one of the lowest grades of energy, and this is what is involved in heat transfer. So this is the thermal energy in transit due to spatial temperature difference. So this is the most important thing for heat transfer to take place. There should be temperature difference. So unless there is no temperature difference, heat transfer will not take place. No matter how hot a body is, for it to exchange heat with another body, there should be some temperature differences. For example, two bodies which are at a temperature of 3000 degrees Celsius, each are having 3000 degrees Celsius, will not exchange heat because both are at the same temperature, no matter how high that temperature is. So the temperature difference is important, unless otherwise there will be no heat transfer taking place at all. So here there are three modes of heat transfer shown. Conduction is the first one, simplest one. Convection is slightly complicated compared to conduction. And finally the radiation, which is the most complex one. So here there is an example of a conduction through a solid or a stationary fluid. You see here there is this solid object. You can take this as a wall. Let us say you have a room in a building, and one side of the room, the outside of the room, is subjected to solar radiation. Let us say it is facing east side and it's receiving direct radiation from the sun in the morning, and one side is hot. So T1 is greater than T2. Let us say this side is subjected to solar radiation and is hot, and this side of the wall, which is the inside of the room, is at a lower temperature because you are running an air conditioner. So there is a temperature difference. High temperature on the outside, let us say this is at 40 degrees Celsius and this side is at 25 degrees Celsius. So in such a case, heat transfer takes place from high temperature to low temperature through this wall. So heat conduction is something that takes place through this solid surface, solid material or a stationary fluid. So sometimes this particular material doesn't have to be solid, it can also be liquid, and conduction will be the predominant mode of heat transfer provided this liquid is stationary. So that is an important condition. So heat transfer
So,
across a certain, yes.
so what if it's a poor conductor of heat like plastic or something?
Yeah, when it is a poor conductor of heat, what happens is the temperature difference between the high temperature side and the low temperature side will be very, very high. So even if the outside temperature is at 40 degrees Celsius, inside temperature will be at 25 degrees Celsius, even if there is no air conditioning. Let us say this particular material is made out of good conductor like copper, like silver, like aluminum, then outside and inside temperatures will be very, very close. If it outside is 40, inside maybe 37, 38 degrees if it is a good conductor. Okay, so depending on the material and its properties, the temperatures across will also be different. Okay.
Okay, sir.
So usually when we talk about a wall in a room, we can cite this example: high temperature on one side, low temperature on the other side. But sometimes we'll also have a fluid here, stationary fluid. For example, let us say, have you heard of double pane windows? In some houses there will be windows, but the windows will have outside surface and then into a glass. And that window glass will have an outside surface and an inside surface. That means one glass sheet will be on the outside and another glass sheet will be on the inside. And in between these two glass sheets, there will be air trap. So that air is, let us say, if the thickness of that column is very small, then the air will be stationary. So in such cases, there will be conduction, heat conduction through the fluid also. Now coming to the convection, the phenomenon of convection. In convection, there should be two things involved. One, convection from a surface to a moving fluid. There should be a surface and there should be a fluid that is moving. So a solid surface is compulsory as far as convection is concerned. Along with that, there should be a fluid. That means there should be two phases. One is a solid phase, and another one is a liquid or a gaseous phase. So in such a case, when we have solid at a surface and some fluid is moving over the surface, then if the surface temperature is greater than the fluid temperature, then heat transfer will take place from the surface to the fluid. So this is a classic example of convection. For example, we have a hot plate which has just come out of the furnace after heat treatment. That plate has to be cooled under forced convection conditions. Then what we do is we put that hot plate on a surface and place a fan along its so that the air is blowing along the length like this. So there we have a classic case of heat convection. Okay, so there the principles of convection have to be applied. Now here you see there is this moving fluid shown, and the temperature of the fluid is represented as a T with a subscript infinity. So T infinity. So this notation is commonly used to represent the free stream fluid. That means the fluid flowing over a surface. So this is the free stream temperature. So the same notation we have used while studying fluid mechanics when we are discussing the boundary layer concept. Okay. Now, in conduction and in convection, the heat transfer is always from a temperature of a high, from a surface of higher temperature to another surface of lower temperature, or from one entity at a higher temperature to another entity at a lower temperature. That is common to conduction and convection. Coming to radiation, there is a difference. You see here, the titles here, conduction through a solid, convection from a surface. But when you come to radiation, there is a net, the word net is used, net radiation between heat exchange, net radiation heat exchange between two surfaces. The reason is, radiation is a phenomena which occurs for any surface or any object or any entity whose temperature is above 0 Kelvin. That means anything above 0 Kelvin or anything above minus 273 degrees Celsius, that surface or that object or that entity will radiate heat.
Excuse me, sir.
You can imagine very, very cold objects also will radiate some heat. Yeah.
Sir,
Yes.
one student wants to join this class, sir. It seems that he can't join. You have to
Yeah.
accept his request.
I should accept.
Yes, sir. 19 BME 1292, sir.
Um, I'm not able to see any request here. See, not able to see any request actually. See, you can. I have shared a link. You can give it to him, and he will be able to join. So that's the link
Sir,
to join
he
directly.
joined and he's
Sorry?
telling that he joined through that link only, sir. And he's telling that you have to accept the
Yeah, but I'm
request.
not seeing. I didn't get any request for accessing. I didn't. I'm not able to get any access request. That's the thing. I don't know where to accept.
Okay, sir. I will ask him, sir.
Yeah, just inform him. So that's you can share that link, but I'm not getting anything to accept. I don't know where. Okay, there is some message. Let me see. Okay, got it. All right. I think now he should be able to add. He should be able to join. All
Thank
right.
you, sir.
Are you able to see my slides still? Are my slides visible?
Yes, sir.
Okay. So we have here two surfaces, and each of these surfaces are at a different temperature. One surface is at T1. This surface is at T1 temperature. Another surface is at T2 temperature. The beauty about radiation is that any surface which is above 0 Kelvin or above minus 273 degrees Celsius will emit radiation. So what is happening here? This surface is emitting radiation and this surface is emitting radiation. Ultimately, let us say T1 is greater than T2, assuming. Then the radiation emitted by T1 minus the radiation emitted by T2 will be the net radiation exchanged between T1 and T2. So if surface T1 is hotter than T2, then the radiation emitted by T1 is greater than that emitted by T2. Therefore, we have to subtract one from the other to evaluate the net radiation. So that is what needs to be done for radiation concepts. Okay. So just remember, anything above 0 Kelvin will emit radiation, and at 0 Kelvin, which is theoretically impossible to attain, but we can approach that, especially in the outer space. The temperature is 0 Kelvin. So in such cases, there will be any object at that temperature will not emit any radiation. It's a kind of a dead state. Okay, where do we apply this heat transfer? So the three forms of heat transfer, in one or more forms, there will be several applications. For example, in the human body itself, the way we maintain our body temperature, surface temperature, is by heat transfer. Our body temperature is different from the ambient temperature. So whenever there is a difference in this, either we our body will take some action so as to maintain the body temperature constant. We are warm-blooded creatures, warm-blooded. We are mammals, warm-blooded. Therefore, we maintain our body temperature constant. So, if there is any difference between our surface, our body temperature and the ambient temperature, then our body takes some action so as to maintain our body temperature constant. So, either it absorbs heat or rejects heat, or metabolism changes. Then we have air conditioning systems. Air conditioning systems, we have this the vapor compression, have a condenser and evaporator, which exchange heat with working fluid. There will be working fluid, the refrigerant, which will absorb heat in the evaporator and reject heat in the condenser. There we have a heat transfer process taking place. Then we have these heating systems. For example, we can take the case of your water heater or the geyser in your bathroom. So we are getting a continuous stream of warm water because there is a heater which is supplying heat, and that is heat is transferred to the water that is flowing through the pipeline. In the electronic equipment, yesterday I gave you an example of how the personal computers about 25 years ago are different from the personal computers that we use now. 25 years ago, the heat transfer studies in electronic circuits, electronic units, enclosures is not that well developed, and therefore we had to employ air conditioning to operate that. But now we don't need air conditioning now because the heat transfer capabilities are better. But if if the amount of processing is extremely large, and if the amount of heat generated is extremely large, then we still need heat transfer surfaces. You must have heard of servers of these big tech companies, Google, all these servers located all over the world, or Facebook servers and so on, which store a huge database, and they have a continuous traffic, and therefore they are continuously working. Because of that, the processing, lot of heat is generated, and for them, it is mandatory to have some kind of a cooling system. So they should employ a cooling system and to keep the servers cold. And then the power plants. In power plants, we have boiler, we have a condenser, where there is a heat transfer taking place between the working fluid, which is water, and in the boiler, it is the heat transfer between the flue gases of combustion and water, and in case of condenser, it is the heat transfer between cold water and hot water. Then in the refrigeration systems, which is similar to the air conditioning systems, there is an evaporator and there is a condenser where heat transfer is taking place. Okay, so you can actually you see any equipment and you will see some form or other of heat transfer phenomena taking place in that particular equipment. So what are the modes of heat transfer? There are three modes of heat transfer as we have seen: conduction, convection, and radiation. So this is what you have also learned in your elementary schools, elementary classes in high school or +2. So these three phenomena. So conduction and convection need a medium for heat transfer. So these two phenomena, first two, they need a medium for heat transfer. Unless there is a medium, heat transfer will not take place. That means there won't be conduction and convection in vacuum. Therefore, in outer space, there is no possibility of conduction and convection. But radiation does not need a medium for heat transfer. So for radiation to occur, in fact, if there is a medium, the radiation, the amount of heat radiated will actually attenuate, will actually reduce in the presence of a medium. Therefore, for radiation to take place in its full force, there should actually be no medium. That's when the radiation works best. So radiation actually does not need a medium. Therefore, in the solar radiation is traveling from the sun to the earth through a vast space, which is basically vacuum. After traveling through the vast space only, it is entering the Earth's atmosphere, and there it is getting attenuated. And fortunately for us, we are in Earth, which is properly placed in the solar system, so that we have the right temperature for life to survive and sustain. So this is one aspect of radiation. It doesn't need a medium, and in fact, if there is no medium, it works best. So here is an example of demonstrating how these three phenomena are functioning. Okay. Now let us say there is a barn on fire. So there's a village and there's a barn where you store these food grains, and this barn is on fire. So if you want to put out this fire, you need to use water. So if you see, if you are using the first method, for example, you have a pump and you have a nozzle, and from this location you are directly striking directly able to pour water on the fire directly from the well onto the barn, then that means you are not depending on the medium that is present in between these two. That means this particular phenomena, example number 1, is the example of radiation. So whatever is there in between doesn't matter. The point of source and point of receiving, these two are to be, they can be connected with this particular water. So this is how radiation works, irrespective of whatever is there in between. Then the second one is conduction. You see, you can carry water with the help of a bucket, and we have a line of people, each one carrying water from one point to other point and handing it over to the next person. So from one point to other point, the conduction takes place up to the barn, and the last person will throw the water on the barn. So this is how the conduction works, point to point movement of heat. Lastly, convection. In the convection, there is only one person who is doing all the running from the well to the barn. So here, this person carries water from the well and runs to the barn and then pours it over. So this is how the convection works. So this is a rough example of how these three modes of conduction are can be analogous to this example of putting out the fire in a barn. Now coming to the first mode of heat transfer, the conduction. Conduction is the transfer of energy from more energetic particles of a substance to the adjacent less energetic ones. So when we say here energy, we are talking about thermal energy. So conduction is a transfer of energy, heat energy, from more energetic particles. That means particles having higher thermal energy of a substance to the adjacent particles with less energy. That means cooler particles. So heat transfer takes place from higher energy particles, the adjacent ones only. It cannot travel quite far long distance, so it can only transfer energy to the adjacent, like this example. So that is what is we call it as a conduction. It can take place in solids, liquids, and also in gases. But predominantly it is taking place in solids and to certain extent liquids. Mostly in gases, the conduction mode of heat transfer is very small. It has got a very small contribution compared to convection and sometimes radiation. And also one important aspect of radiation is that it comes into play. You will see the governing equation for radiation. It comes into play whenever the temperature is greater than or equal to about 500 degrees Celsius. That means radiation is a phenomenon which takes place at higher temperatures only. So that is one aspect of radiation. Uh, you must have seen a blacksmith working with a hot rod of iron. Initially, when the rod of iron is at room temperature, it is brown or blackish in color. But once it is started to heat in the fire, then it starts changing color. Initially, it takes the red color and becomes bright red, and then it becomes whiter in color as it becomes hotter and hotter. So this change in color is because of the change in temperature. So at different temperatures, the radiation evolved or radiation emerging is at a different wavelength, which has got a different color. Okay, so even though conduction can take place in solids and liquids and gases, it's more predominant in solids, to a certain extent in liquids, but very rare in gases, or very small in gases. In solids, conduction is due to a combination of a vibration of molecules in a lattice and energy transported by the free electrons. So this is an explanation from the physics of the material molecular arrangement and lattice vibrations and so on, how conduction is taking place. It's due to a combination of vibration of molecules. Molecules vibrate in a lattice and then energy transported by the free electrons. So there are molecular activity as well as electron activity or electron movement is responsible for the conduction. That is in solids. In liquids and gases, it is due to the collision and diffusion of molecules during their random motion. Okay, so this phenomena is explained in this figure. You see here three different materials: solid, liquid, and gas. So in solids, we can see that there is a very orderly arrangement of molecules. So we have these molecules. The molecules vibrate or lattice vibrations takes place because of the energy, higher energy, which is acquired in this case because of a higher temperature. So heat conduction is because of the lattice vibrations and also flow of the free electrons. So these free electrons which are moving within the material, so that is responsible for the conduction of heat. So as they move, as the free electrons move, they carry this heat from one location to other location. It's usually the location of higher temperature to location of a lower temperature. When coming to the liquids and gases, the reasons are different. Here, the arrangement of these molecules is not as orderly as it is, and they are in a constant motion. They have certain freedom to move larger distances. Here, these molecules they vibrate about a fixed location, but in the liquids and gases, that freedom to move is much larger, and therefore the arrangement doesn't appear to be as orderly as in the solids. So in the liquids, the heat conduction is because of one reason is molecular collision, because these molecules are free to move. They also collide with each other, and because of the random motion. And another one is called as a molecular diffusion. So the same reasons hold for gases also, molecular collisions and molecular diffusion. Now, what you can see or observe in this molecular arrangement is that in the liquids, the intermolecular space is smaller compared to that in gases. That means the chances of molecules colliding with each other are higher in the liquids than the chances in a gas, because they have a lot of free space. So their movement may not always result in collision in gases, but there is a high probability of collision in case of liquids. So because of this, the heat conduction capabilities of liquid are greater than the heat conduction capabilities of a gas. So that heat conduction capability is termed as a thermal conductivity. So this is the phenomenon called as the thermal conductivity. That means the ability to conduct heat. So different, it is a material property and it is different for different materials. So good conductors will have a very large value of thermal conductivity, whereas the poor conductors will have a very small value of thermal conductivity. In engineering, we are interested both in good conductors as well as bad conductors. So whenever we want to transfer heat effectively, we go for good conductors, whereas when we want to prevent heat loss, we prefer to use bad conductors. So we need to have a database of all the good as well as the bad conductors. So now coming to the law that governs the heat conduction. So that law is called as the Fourier's law. Fourier law, whatever you can call. Fourier's law of heat conduction. It gives the rate of heat conduction. So this particular slide deals with the rate of heat conduction. So how to quantify the amount of heat conducted. So Fourier is the one who has put out this law based on physical observation and understanding of conduction. So this is the law, and this equation is not derived from any fundamentals. So it is posed as a law, and we accept it and take it and use it. So how does it say? What does it say? For, let us say, we take a slab of a material, and one side of the slab is at a temperature T1 and another one is at a temperature T2. Now you can see T1 is at a higher elevation than T2, which implies that T1 is greater than T2 in this case. So left side is hotter than the right side. So according to the principles of heat transfer, heat flows from a high temperature side to the low temperature side. So therefore this arrow indicates the flow of heat from the high temperature side to the low temperature side. So in this case, the heat is flowing from the left to right. Now there is a thickness of this wall. That thickness is called as a delta X. And there is a temperature gradient here. T1 is the left side temperature, T2 is the right side temperature. So there is a temperature difference. T1 minus T2 is the temperature difference. And this temperature difference is taking place across a certain thickness, which is delta X. So change in the temperature divided by the change in the thickness is called as the thermal gradient. So these things are used in the equation. So A is the surface area of one side, and in this particular example, both the surfaces are having the same area on both sides. Okay. So this is a typical example of a one-dimensional heat conduction. So heat is conducted only in one direction, only in the X direction. There is no heat conduction shown in the Y direction and Z direction. So that we shall see in the subsequent modules. So for such an arrangement, the heat conducted, now you see here heat is represented by a symbol Q, a capital Q. Subscript COND stands for conduction, and there is a dot on top of Q. What does the dot signify? That dot signifies the rate. So the rate of heat conduction is equal to minus, there is a negative symbol here, minus K. K is a material property called as the thermal conductivity. So it depends on depends on the material. Different materials have different thermal conductivities and also thermal temperature. Then it's also depending on the A. A is the area available for heat transfer, and it is also dependent on this dt by dx. dt is the temperature gradient, temperature difference. Dx is the distance, incremental distance. So thermal gradient dt by dx is the thermal gradient. You see thermal gradient T1 minus T2 divided by delta X, or in this case dt by dx. How do you evaluate? We'll come to all those details in a short while. So this is basically the law of heat conduction. So this is what determines the heat conducted in a particular situation, and this law is named after Fourier, and it's called as the Fourier law of heat conduction. Okay, we use this equation. Now let us come back and look at this equation much closer. You can see that heat conducted is directly proportional to the conductivity, the area, and the thermal gradient. That means when the conductivity is high, heat transferred will be high, heat conducted will be high. When the area is high, heat conducted will be high. And when the thermal gradient is high, then the heat conducted also will be high. Now, what is this thermal gradient? For this thermal gradient to be high, the numerator must be high and the denominator must be low to make it very big quantity. That means the temperature differences must be high. That means left side should be very hot and right side should be very cold, and dx should be as small as possible. That means if this thickness is very, very small, then this thermal gradient will be very, very large, and very large thermal gradient will result in high heat conduction. So these three parameters influence the heat conduction. Thermal conductivity is a material property. Area available for heat transfer is a geometric property. And the thermal gradient is depending on the situation. Okay, so based on this, we can calculate the heat conducted. Now coming to this minus sign, the minus sign in this equation plays a significant role or indicates a very important phenomena. Now you see here, this is the origin and this is the x direction. X direction is to the right. So when we want to evaluate the thermal gradient dt by dx, dt is the change in the temperature. But always in engineering, change is always final minus the initial. So dt is actually T2 minus T1. T2 minus T1. Now dx is the thickness at this point or the length at this point minus the length at this point. Okay, length at this, since we are measuring x in the rightward direction, the length at this point is greater than the length at this point. That means dx will be a positive quantity. But dt, since T2 is lesser than T1, dt will be a negative quantity. So in this situation, dt by dx will actually be a negative quantity. So to make this heat conducted positive, we deliberately introduce a negative symbol here. So this negative symbol will counter the negative symbol in dt by dx and make it positive. Okay, so for this situation to be represented, we have to use this negative symbol because dt by dx is a negative quantity because T2 is smaller than T1. So T2 minus T1 will be a negative quantity. So dt by dx is the thermal gradient, and the equation implies that heat transfer in the direction of a decreasing temperature. So heat is transferring in the direction of the decreasing temperature. So the final temperature or the farther temperature is smaller than the nearer temperature, and therefore dt by dx is negative. Thermal conductivity is the rate of heat transfer through a unit thickness of material per unit area per unit temperature difference. So this is how we define. So what is this? Is the rate of heat transfer through a unit thickness of material per unit area per unit temperature. So unit temperature difference, unit thickness, and unit area. That means dt is equal to 1, dx is equal to 1, and area is equal to 1. When that situation occurs, then the thermal conductivity will be equal to the rate of heat transfer. That's what this implies. The high value of K indicates a good heat conductor. So bigger value of K has more value it is in magnitude, it is a better conductor. Lower value of K indicates a poor conductor, or it's also called as an insulator. We need good conductors, we also need insulators. Copper and silver are good conductors, while rubber, wood, styrofoam are bad conductors. So we are giving some examples here. Copper and silver are good conductors. In fact, silver is among these two, silver is the best conductor. But usually, silver being expensive, we don't use silver, but we go for copper for commercial applications wherever we need good conductors. Similarly, we need bad conductors. For example, in case of refrigerators, refrigerator is a small space which is kept at a temperature much below the ambient temperature. Therefore, for that space to remain cool, we have to minimize the heat transfer from the ambient into the refrigerator. So for that, we use insulators. For example, in refrigerators, we use something called as the styrofoam, which is some kind of a synthetic material. So this is a bad conductor. So here are some examples of different kinds of materials and their thermal properties. Now you can see here, which is the thermal conductivity has the unit of watt per meter Kelvin. watt per meter Kelvin. So this Kelvin also is in the denominator only. Meter Kelvin is in the denominator, and sometimes you may also be given this unit as a watt per meter degree Celsius. So both are same, watt per meter Kelvin or watt per meter degree Celsius is same, because 1 Kelvin is equal to 1 degree Celsius. Now diamond has got a value of 2300. See, it's an extremely good conductor, but we can't use diamond for good conduction applications because of its cost. Next comes silver, about 429 watt per meter Kelvin. Copper, next one, 400 watt per meter Kelvin. Gold, 317, again expensive, so cannot use for commercial applications. Aluminum is a 237. It's a decent conductor, and therefore we find, as far as good conductors are concerned, we find aluminum as the material of choice. One reason is it is a good conductor, and another reason is aluminum is lighter in weight and it's not expensive. So aluminum application in engineering are quite common. Then comes the poor conductors. You see, glass has got a poor conductivity 0.78. Therefore, whenever we want poor conduction or insulation, some applications use glass. Human skin is a poor conductor, 0.37. Thankfully, it's a poor conductor. Wood is much less, 0.17 watt per meter Kelvin. Air, much less, 0.026. So we use air sometimes to act as an insulator. In cold countries, extremely cold countries and extremely warm countries, the walls of a room will have an air chamber. So that prevents the heat loss or heat ingress from high temperature to low temperature. Then we also have urethane, which is almost same as that of air. So here there is a graph showing the variation of thermal conductivity with respect to temperature. So on the x-axis we have temperature, and on the y-axis we have the thermal conductivity. Now we can see that the thermal conductivity in general, what is happening, the thermal conductivity is decreasing with respect to temperature. So as the temperature is increasing, thermal conductivity is decreasing. Now we see here three different lines. The solid line implies solids, dashed line implies liquids, and dotted line implies gases. So you can see in general, the solid lines are on the top. That means the solids are actually having high thermal conductivity compared to liquids. So here you see water. Now here you see aluminum, that is after melting, it is taking the liquid form. Similarly, silver and copper have this phenomenon. Okay. Water is having much lower thermal conductivity compared to liquid aluminum, liquid silver, liquid copper, liquid gold. And gases are at the bottommost point. Helium, carbon tetrachloride, steam, air, and argon. So one thing we can immediately recognize from this graph is that solids have the highest amount of thermal conductivity and liquids have gases have the least amount of thermal conductivity in general. Now, comparing the behavior with respect to temperature, you can see that for solids, the conductivity is decreasing as the temperature is increasing. You can see here for silver and copper, there is a slight gradual decrease in the thermal conductivity. Whereas for iron and aluminum oxide, you can see there is a drastic drop in the thermal conductivity as the temperature is increasing. As far as liquids are concerned, you can see that liquid thermal conductivity is more or less constant. It's not so strongly influenced by the temperature. So it's more or less constant for aluminum. For silver and copper, the data is not available beyond this temperature. For water, you can see there is a slight increase in the conductivity, and then there is a drop, very slight increase. And remember, this is a logarithmic scale. The x-axis is a linear scale, whereas the y-axis is a logarithmic scale. That means these variations are actually much larger than we can see on this graph. So we can say that the variation in the thermal conductivity for solids is considerable. Now look at the gases. The trend is opposite actually. In the gases, as the temperature increases, the thermal conductivity is actually increasing. So this is opposite to what we have seen for the case of solids. Okay, so this is something you need to keep in mind. Now here is a comparison between two metals, copper and aluminum at different temperatures. 200 Kelvin. 200 Kelvin is a sub-zero temperature. It's minus 73 degrees Celsius. Up to 800 Kelvin. So it's a high temperature, about 500 degrees Celsius.
Sir, in gases, is it because of radiation? Like, is it increasing because of radiation?
No, we are talking about the thermal conductivity. No, radiation is again
Only the
different.
okay.
The thermal conductivity. See, the molecular activity will be extremely large at high temperatures, and the collisions will be large. That is contributing for the higher thermal conductivity. Okay.
Yes, sir, got it.
Now you can see for copper and aluminum, both are decreasing. Okay, so as the temperature increases, the thermal conductivity is decreasing for copper and aluminum. Okay, so this is what you can see for today. I think the time is up, so we'll stop here. If you have any questions, you can ask. Otherwise,
So why does it decrease for solids? Because as the temperature increase, there'll be like less intermolecular forces, so they should be more free to move and transfer heat.
yeah, for solids, it's actually decreasing. See, the molecules are actually quite fixed in solids. Okay, but as you said, it is you're right. It has to increase a little bit, but it's decreasing. I am not sure why exactly it is happening here. It's something to do with the physics of the materials. Okay, so if possible, I'll try and find out why it is happening for solids in that way. Okay.
Okay, sir. Thank you.
Any other questions?
Sir,
Yeah.
sir, you said radiation occurs when the temperature is above 273 Kelvin, no, sir?
Minus 273 Celsius.
Sir,
Or zero, above
zero
zero
Kelvin, no, sir.
Yeah, yeah.
Sir, if a process like convection or conduction occurs at the temperature above zero Kelvin, radiation occurs during the process itself, sir.
Yes.
Okay, sir.
Yes. See, radiation always takes place whenever the temperatures are above 0 Kelvin. How much quantity is always a question. Most of the times, when the temperatures are below 500 degrees Celsius, the amount of heat radiated, net heat radiated, is smaller than the amount of heat conducted or heat convected. So in such cases, we neglect radiation. We neglect radiation because it is lesser in quantity, and also you will see from the mathematical equation of radiation law, you will see that radiation is something mathematically difficult to deal with. You will understand that later on in subsequent classes. So because of that, we neglect radiation, the amount of radiation. But there are situations where radiation has to be considered. We will see all those things in subsequent classes.
Thank you,
Okay.
sir.
All right. All right, then I'll stop recording